Good morning everyone. Today we will see how to obtain this kind of surface here. It is a very easy tutorial and it can be useful to obtain several surface that will be driven by these two Grasshopper here. So you can really decide the shape using this Grasshopper here and this Grasshopper here. Is based on a geometry of two attractor point, and the attractor point are located one here and one on the center of this wave here. Okay, you can use it to move to decide the shape of your surface. So let's start creating rectangular curve that we define our canvas. Then we create a boundary surface. Let me show on shaded view. Then we divide this surface by 98 point in U and 98 in V direction. Then what we do is define how much it will be the Z movement of each point. So I'm going to move this point, but the point is how much I have to move this point in Z direction. And to do this, we start from the distance from the first attractor point. We define this attractor point, so with the right click of the mouse we set one point. So we define the first attractor point, that is this one, then the second attractor point, that is the one on the left. Oh, it was the inverse, but no problem. So this is the first attractor point. Then I'm going to connect each point of the grid with my attractor point. So we have a lot of line here, and I'm going to evaluate the length of each line using curve length. Then I use boundary to evaluate the domain that encompasses all these values, but it's very important to use flatten before use it. So I have that all the length are encompasses on this domain. Then I'm going to remap all the length that are encompasses on the domain, the source domain that we just created, and I project these values on a domain of from 0 to 1. In this way I can enter directly into a Grasshopper that have this kind of domain, so from 0 to 1, and I select with the right click graph types sine summation. I use this kind of graph here, and basically I do it for the first attractor point. Then I will do the same with the second attractor point. So I create a line that connects each point to this attractor point. I evaluate the length of each line. I evaluate the domain that encompasses all the line length, and then I remap all the numbers coming from line length to the domain that is to the target domain, that is from 0 to 1, and then I apply a graph mapper just like before. But the the result is I use the result to enter into this simple addition component, and then I'm going to remap neatly these values inside a domain that this time is not from 0 to 1, it's 0 to these values that I define with a slider, that basically will define the thickness of the piece of wood that I'm working. You know that I'm working with milling machine, 5-axis milling machine. So then I use this this slider in order to amplify the effect, but you can also not use it. And then I enter inside Z. I apply Z to the move component. The input G of the move component is basically the result of divide surface, the point resulting from divide surface. So this is our results that depend on Grasshopper 1, Grasshopper 2, and position of the attractor point. Now, simply I apply this surface from point coming from flexibility plugin here, that is free and you can download from Food for Rhino. And in UMV you can use the values coming from S divide. It's the same values that we used to input into S divide. So in UMV we will use the same values that we have used here in S divide, and this is what we obtain. Regarding the preview, we simply apply this material that is coming from a Rhino directly. So I defined previously a Rhino, a metal material, and then I apply in Grasshopper. Thank you for watching, have a nice day and a good work.